In this tutorial, I'm looking at 2022 Paper 1 Question 10, and we're talking about logs and a bit of differentiation. We're given a function that represents the proportion of numbers that a student can memorize after t hours. We're asked to work out what proportion of the numbers does the student remember after 3 hours. That simply means instead of a t, you sub in a 3. And if you plug this into your calculator, the proportion of the numbers that the student remembers is 65%, or 0.65. In part B, we're asked to work out after how many hours is the proportion of the digits that the student can remember 55%. In other words, you take your equation, you let it equal to 0.55, and you try to solve for t. So the first thing we need to do is isolate the term with the t in it. So the first thing I did was subtract I subtracted 0.82 from both sides. This becomes minus 0.27. Then I wanted to isolate the ln t plus 1, so I divide both sides by minus 0.12. And I end up with ln t plus 1 equals 2.25. It's probably here that students might struggle. Remember what ln represents. ln represents log to the base e. Okay, so what I actually have on the left is log t plus 1 to the base e is equal to 2.25. And then in the top right hand corner of page 21 in your maths tables, it tells you how to deal with this. You should remember that to get rid of the log here, that the base to the power of the answer will give you the thing in the brackets. In other words, e to the power of 2.25 is equal to t plus 1. And obviously that's what I wanted to do because now the log is gone. In order to get t on its own, I simply subtract 1 from both sides. So t is equal to e to the power of 2.25 minus 1. And now all I'm going to do is plug that into my calculator and get my final answer. So if you plug it into your calculator, t works out as 8.49 hours. So after this many hours, the student will only remember 55% of the digits. In C part I, we're asked to find the value of p-1. So you should recognize the little dash indicates the derivative. So you need to get the derivative and sub in t equals 1. If you differentiate 0.82, you just get 0 because it's a constant. And there's a rule in our maths tables for getting the derivative of a log. The derivative of ln of t plus 1 is simply 1 over t plus 1. That rule is there in your maths tables. And then you multiply by the derivative of t plus 1. The derivative of t plus 1 is simply 1. You'll notice that the second term here had a coefficient of minus 0.12, so you just take it down. So you just take down your coefficient, the derivative of log of something is just 1 over what was in the brackets, multiplied by the derivative of t plus 1, which is 1. Then you can rewrite that. All I've done is simplified that a little bit. Rather than writing it like this, I can write it with the top of the fraction is minus 0.12, the bottom of the fraction is t plus 1. That's the derivative simplified fully. The question asked me to get the derivative when t equals 1, so you simply sub in t equals 1, and when you do that, if you plug it into your calculator, your answer is minus 0.06. In C part 2, we're told that when t is between 0 and 12, the first derivative is always decreasing. And we already know that from C part 1 anyway, because the top of the fraction is negative. And if I'm subbing in a positive value for t, the bottom of the fraction is always positive. If the top is always negative and the bottom is always positive, then the fraction is always negative. We're asked what we can deduce from this. And that means that since the first derivative is always negative, it means the slope is always negative. In other words, the proportion of digits recalled is always decreasing. So the longer it is, as t increases, the longer it is since you memorized the digits in the first place, the less that you know, because consistently the proportion that you remember decreases with time. So we already have the first derivative. From the previous part of the question, we know the first derivative is minus 0.12 over t plus 1. We need to differentiate this and prove that the second derivative can't be equal to 0. Now before I differentiate this, I'm going to rearrange it a little bit. Like you could use the chain rule, you could use the quotient rule now, but I think there's an easier way of doing it. So the way I'd suggest doing this, I'd rewrite this as minus 0.12, and then you have t plus 1 to the power of 1 on the bottom of the fraction. One of our rules of powers from page 21 in our maths tables tells us if you've 1 over a to the power of p, you can rewrite that as a to the power of minus p. So if I have a t plus 1 to the power of plus 1 on the bottom, I can rewrite that as t plus 1 to the power of minus 1 on the top. All I'm doing is I have like a to the power of p and I bring it up, it becomes a to the power minus p. I have t plus 1 to the power 1, I bring it up, it becomes t plus 1 to the power minus 1. The reason I'm doing that is because now it's really easy to differentiate. I'm going to use the chain rule now. So if I'm using the chain rule, you treat this as if it's just something to the power of minus 1. If you're differentiating, you just bring your power in front. So I'm just going to multiply minus 1 by minus 0.12. I'm just bringing my power in front. Minus 1 by minus 0.12 is plus 0.12. Then I have t plus 1 and I decrease the power by 1. So this to the power of minus 1, if you differentiate, you decrease the power by 1, so it becomes to the power of minus 2. And now I multiply by the derivative of what's in the brackets. The derivative of t plus 1 is simply 1. So that's another way of doing it rather than using the quotient rule. I can now rewrite this. Rather than having the t plus 1 to the power minus 2 on the top, I'm going to use this rule, except I'm going to go from the right hand side to the left hand side. I'm going to leave the 0.12 as it is, but t plus 1 to the power minus 2 is the same as t plus 1 to the power of 2 on the bottom of the fraction. So all I'm doing is reversing that rule of powers. So the second derivative simplified fully is this. Now, I suppose all I have to do is prove that this can't be equal to 0. One way of doing that is I could just do this as an equation and try and let it equal to 0. So let's just see what happens if I let my second derivative equal to 0, what happens? Imagine if I was trying to solve this. The first thing I would do is I would try and get rid of the fraction. In order to get rid of the fraction, multiply both sides by the denominator. So what I might do next is multiply both sides by t plus 1 to be squared. If you multiply the left-hand side by t plus 1 to be squared, you get 0.12. If you multiply 0 by t plus 1 to be squared, you get 0. So if I do that, I end up with 0.2 equals 0. That doesn't make sense. Obviously 0.2 is not equal to 0, so the thing I did on the previous line is impossible. In other words, it's impossible for the second derivative to be equal to 0. If it's impossible for the second derivative to be equal to 0, I can conclude that there are no points of inflection. Okay, in part E, you're given this equation, a equals b times t plus 1 to the power c. You're told that A represents how well you can do a skill if you practice it, and B represents how well you can do that same skill t months later. So basically, A is how good you are initially, B is how good you are a couple of months later, or t months later, and C is a constant. In this question, we're asked to get C on its own. So we need to isolate the C. We want to get C in terms of log A to the base 10, log B to the base 10, and log t plus 1 to the base 10. So you have to look at this and realize that the initial problem is that the C, the unknown, is in the power, which means it's absolutely a logs question. So we're going to have to introduce logs to get the C out of the power. That's the only thing we could possibly do. But before we introduce logs, we have to isolate the part of the expression with the unknown in the power. In other words, we have to isolate the t plus 1 to the power c. So step 1, divide both sides by b. If I divide the left by b, I get a over b. If I divide the right by b, I get t plus 1 to the power of c. Now that I've isolated that, I'm going to introduce logs. And usually what I would do and what a lot of students would do is introduce the natural log ln. But obviously I'm not going to introduce the natural log this time because I can see that my answer needs to have a log to the base 10 in it. So rather than introducing the natural log, we're going to introduce log to the base 10. And it's quite simple. You just literally put in log to the base 10 in front of the left hand side and you stick in a log to the base 10 in front of the right hand side. That's all you do. The reason we introduce logs is that now we can apply the rules of logs. I can use a rule of logs to simplify this, and I can use a rule of logs to simplify this. If you go to page 21 in your maths tables, the column in the middle, the second rule allows me to simplify this. Instead of log a over b to the base 10, I can split that up into log a to the base 10 minus log b to the base 10. In other words, it's just the top of the fraction, it's the a minus the b. So I've split the left hand side into 2. And the whole point of introducing logs was to get rid of the c in the power. The third rule on that same page tells me if I have log of something to a power, I can just bring the power in front. So I can rewrite this as c times the log of t plus 1 to the base 10. Now, my final step, I simply want to get c on its own. So I'm going to divide both sides by log t plus 1 to the base 10. So the left-hand side will be log a to the base 10 minus log b to the base 10 divided by everything that c was multiplied by up here. It's going to be log t plus 1 to the base 10. And there we have it, c in terms of log a to the base 10, log b to the base 10, and log t plus 1 to the base 10. In part 2, we have to actually put that into practice. So we're using the same formula. We're told that initially this person got 80% in a Qatar exam, but 2 years later the person got 47% in a Qatar exam. So that represents the decline in ability, or the decline in the ability to do the skill. T is in months and B was 2 years later, so obviously there's 24 months in 2 years, so T is 24. So how I started this off, I just subbed in A, B and T. I subbed in the variables, the values given in part 2, and then we've got one equation and one unknown. So the way that I decided to do this was, it's very similar to what we did in part 1. We're trying to get C on its own. C is in the power, so the unknown is in the power, which means it's a logs question. So the first thing we have to do is isolate the bracket, the 24 plus 1 to the power of C. So step 1, I divided both sides by 0.47. The left becomes 0.8 over 0.47, and then 24 and 1, I get 25 to the power of C. Now that I've isolated this bit, I introduce logs. I decided to introduce the natural log ln, but you can introduce whatever log you want. If you want to introduce log to the base 10 or log to the base 5 or whatever, it works. But I'd be always inclined to use ln. I introduce ln on both sides, and then the third rule of powers, or logs, tells me if I have log of something to a power, you can just bring the power in front. So ln 25 to the power of c becomes c ln 25. Simply to get c on its own, you divide both sides by ln 25. So I get c is what was already on the left divided by ln 25, and if you plug that into your calculator to 3 decimal places, your answer is 0.165.